Hello students, welcome back. We just completed proving this formula, this one, and before that we completed this one. Let's work on the rest of the formula here. Okay, this is the definition. Let's copy and paste it down here. And then I want one more, translation principle. Let's copy it here, even above the definition. Here's a reminder. How did you prove it? Well, we multiply the exponential times the original function, and then this was inside this Laplace transformation, this exponential, and then this exponential on the other hand came from the definition. It was there before. Now we have two exponentials here. Put these two together, what do we get? We get this simplification, which I just highlighted in purple. So blue, red combined, we have this purple. And compare this integral here with the definition of the Laplace transform. The only difference is s minus a versus s. Therefore, instead of the Laplace transform capital Y of s, I'm getting capital Y of s minus a. What made the difference? This exponential, e to the at multiplication. That was the key. Remember that, and let's go to here. Now please note that this is e to the at times 1. That fits into this category right away. Maybe I should increase the font. Basically it's this, e to the at power times 1, and because of this being the translation, and we have Laplace transform of 1, so we have s minus a replacing s in place of the first formula, and that's how you get s minus a. Of course, you can calculate this integral directly. You can get the same result as well, but I prefer to use this principle of the translation principle. How about the next formula here? Do you also see a translation? T to the nth power here. Now t to the nth power times exponential. Hey, that's a translation. We exploited it before. In place of s, we have s minus a. So we have t to the nth power times the exponential. The exponential is creating the translation. That's what we have here. Now we have two more formulae here, which I'm postponing. And then let's go to these two. We have exponential times cosine. Now, formula for cosine is here. That's Laplace transformation formula for cosine. And then we multiply e to the at. That's translation. So in place of s, we have s minus a. And in place of this a, we have s minus a again. It's translation again. This one again. How about this versus that? Again, the same deal. We're multiplying by e to the at power. It's translation. So translating this one, s is becoming s minus a, and that's it. So we completed everything except this one and that one. Let's see. This one was trivially easy, and that was a real challenge. We had to do this integration by parts and so on and so forth. And then all these came from translations. Now these are going to be about the same level as this one. Let's begin. Here's the first proof. And the first proof is based upon this integral computation. Antiderivative of e to the negative st cosine of bt dt is turning out to be, oh my goodness, this expression. I cannot even read it very well. But once you have that, then the conclusion is easy. You can plug in infinity. We have e to the negative infinity. That's 0. That'll kill off everything. And then plug in t equal to 0. Then this is e to the 0 power 1, so it doesn't contribute. And sine of 0 is 0, so that goes away. And cosine of 0 is 1, so that too goes away. What do I have? Top minus bottom, so negative of another minus s over b squared over s squared, this one. So we have the answer. Similarly, we have this situation here. The antiderivative of this e to the negative st sine of bt dt, this computation becomes this computation there. And then if you plug in infinity, that'll kill off everything. E to the negative infinity is 0. Now if you plug in 0, that's e to the 0 power, that's 1. And sine of 0 is 0, so that'll drop out. And cosine of 0 is 1, so you're going to get b over b squared plus s squared. But that's in bottom, so you have the minus minus plus. We have b over b squared plus s squared. We get that. So once you accept this antiderivative, we can do it. But then again, how do you calculate that antiderivative? It goes kind of like this. Start from the original and take the integration by part. U is cosine and v prime is exponential. So we take the antiderivative and then we take the derivative. So by chain rule, we divide by s, the reverse chain rule, and by forward chain rule, we multiply by b. And be careful about pluses and minuses. So we still have exponential times sine, so let's take the integration by parts again. This was there before, and then this is uv, and then we took the antiderivative again, so we have s squared down there, and we take the derivative, so b squared, another multiplication by b, and then we have cosine back again. Now compare this with the original. Exponential times cosine, exponential times cosine, they're the same, except we have different coefficient. So let's simplify the coefficient. There are too many denominators, so multiply everything by s squared to kill off all the denominator. So s squared, this integral, and these two, and then now b squared times that. Same integral, exponential times cosine, but different coefficients. These are like terms. So take the like terms together by flipping this to the other side. Then what do you get? Same integral, b squared plus s squared. And then what's left? These. Finally, divide by this, b squared plus s squared, and then we get this. And this is the antiderivative we have over here, if you simplify a little bit further. If you sit down and try to do this computation, and you're going to appreciate the complexity of this. But in the end, it's just tedious computation, tedious and boring computation going on and on and on and on and on. Very similar computation for sine as well. True integration by parts and taking like terms together and flipping. That's one way to prove it. Another way to prove it, this is the one I prefer a little bit more. We use, well, look at the proof, it's much shorter, so I like it better, but theoretically it's a little bit deeper. We have to use this formula. Cosine of bt is actually exponential e to the ibt plus e to the negative ibt over 2. And this is something we went through in lesson 1a. Cosine of theta is equal to exponential of I theta plus exponential of negative I theta over 2. Let me expand the font a little bit further. This is the formula I'm using. And sine, by the way, is similar, except this is minus and then this is 2i. So I'm using this one here because this is cosine problem. So I have it over there. And let's take the Laplace transformation of each term separately. So 1/2 times this Laplace transform, 1/2 times that Laplace transform. And they're exponentials. So we use the property for exponential. We already did it. So 1 over s minus ib, 1 over s plus ib. They are coming from the exponential, this formula there. And then just simplify these by taking the common denominator. And it turns out these are conjugates. So s plus ib, s minus ib, we get s squared plus b squared in the denominator. And the numerator, plus ib minus ib cancel each other out, and we have 2s. We have 2s, and then this 2 cancel out. We have just s over s squared plus b squared. And that's far simpler and more elegant proof. I like this one better. How about sine proof? Similar, we are using the same formula here. This time we are doing sine. So sine of theta is exponential of I theta minus e to the negative I theta over 2i. We are using this one. Sine of bt can be written as exponential minus exponential over 2i. And then let's do the same thing. Coefficient 1 over 2i out and the Laplace transform of e to the I bt. Coefficient out, Laplace transform of e to the negative I bt. And then these are exponentials, so we can use this formula here. So what do we have? 1 over s minus ib, 1 over s plus ib. These are conjugate, so if I take the common denominator and multiply these two, we have s plus ib, s minus ib, they're conjugate, so we get s squared plus b squared. And then the numerator, what do you get? S plus ib minus s minus ib. This time, s minus s cancel each other out. We have 2ib. And then we have 2i down here and 2i up here. They cancel each other out. And what do we get? We have b over s squared plus b squared. That's precisely wanted. We have it. This is a proof I prefer. This one, yes, it works, but come on, look at this. As a matter of fact, I skipped a lot, even here. But this one, I hardly skipped anything, but I only have 2 lines. Okay, that completes everything, I guess. At least everything I prepared here. But that's not all the Laplace transformation formulae out there. There are more, but whenever other formulae show up, we'll discuss those as they show up. Okay, let's stop here, and that's the end of this lesson.